explicit. There we go. Oop, cancel, share screen. I wonder how YouTube's gonna handle the reproductive system when I go over that for anatomy. Okay, so we're doing chapter 17. What is chapter 17 mainly on? Do you guys know? There's two big concepts. It's buffers and solubility. So we're going to talk about those two concepts. So, pass around a sign-in sheet. Quick. So I can record who's coming, who's not. So take it down, pass it around. You know how it is. Cool. So before I begin, some people already text me. That's nice. Thank you. Okay. So before I begin, what's a buffer do? You guys learn what a buffer does in class yet, or no? Or you guys just totally lost what buffers are? Okay, so I see lots of blank faces, which is concerning. So that's too big of a brush. Let's fix this. Nope, here we go. Thinner, clear drawing, so. Okay. Buffers, the main point of buffers is to resist change in pH. So buffers will stop pH changing from occurring, either going up or down. So what's one way we can increase pH? How do you increase something's pH? You add a base. What's some way you can decrease pH? Add an acid. So those of you who have taken lab already this week or last week should have known about titrations, right? So it's usually pH is up here, or volume is down here. So if you start off anywhere down here, what type of thing do you have? Strong or weak acid? If it's right about here, I'll do a little bit lower. Whoops. Right about here, weak, right? Going up here, if the pH is all the way up there, strong base, weak base. Now, in your guys' test, because in here that talks about titrations 2 or 3 times, so your test might have a question on it. The equivalence point is, or neutral pH is 7. If it's below 7, it's considered an acid. Now, the closer you get to 7, while still being underneath it, it means you're an acid. The further away from 7 you are, the more basic you are, correct? So, if of a titration curve that starts off super low, increases and does that, what 2 things did I titrate? Where did I start off? Strong acid. Where did I end up? Strong base. So I titrated a strong acid with a strong base. Does that make sense? If I started off here, you automatically know that I'm a weak acid, right? And if it only goes up to there, titrating a weak acid with a weak base. That makes sense. Okay. Now they might throw this concept at you. I don't know, but it is tested in the lab final. Is if you see 2 equivalence points, you're dealing with a diprotic acid. If you see 3, triprotic, right? This is going to matter because diprotic acids are very annoying to mess with. You'll figure that out. You guys have taken lab already, know. Okay. Other concepts I'm going to cover real quickly is a buffer. Oops, I want a buffer. Okay, here. A buffer is a weak acid plus a conjugate base, or a weak base plus a conjugate acid. Now, why do I want these 2 things? First off, why is the weak one, why is weak important? What do strong acids, strong bases do? They dissociate fully, right? So if they are formed, they instantly break down and make their products, right? So a strong acid, strong base can never be a buffer because it doesn't stay around to resist a change in pH. Does that make sense? Up next, I want the opposite conjugate one because if I have this right here, a weak acid, its conjugate base, if I add NaOH, what is the NaOH going to go attack? Is it going to attack the base or the acid? What do you guys think? Is it going to attack the base or attack the acid? Which one is it going to attack? It's going to attack the weak acid, right? Because bases and acids neutralize each other, right? If I added hydrochloric acid, what's the hydrochloric acid going to go attack? The conjugate base. Do you see why that's important to have in a chemical equilibrium to form a buffer? This is why buffers have to be a weak acid or a weak acid and its conjugate base or a weak base and its conjugate acid. It's for this reason. We'll see later on, which is the biggest part of this test, is scenarios in which we'll have a buffer and we're adding an acid or a base. We have to draw out the equation a bit differently because of that. Does that make sense? Okay, let's actually go look at some examples. So, how many grams of KOH would it take to neutralize 76 milliliters of that? Okay. So, first off, what I notice is H2SO4, strong or weak? Strong acid, good. What else was special about H2SO4? Look at the hydrogens. How many hydrogens does it have? It has 2. Diprotic acids are awful to mess with because if you have monoprotic acid, guess what you can do? M1V1 equals M2V2. So much easier to do monoprotic acids because of that, right? For strong acids, strong bases. Problem is, we got this guy. This guy can't do that with because he's diprotic. So let's play with them. The equation's going to look like this. KOH plus H2SO4 is only have one-way arrow, right? Theoretically speaking. It's going to make water plus, we're going to make this one react fully. We're not going to make 2 different equations. We'll make one equation. You'll see why. And it's going to make K2SO4. Okay, is this equation balanced, yes or no? No. I put a 2 here, and now it is balanced. Woohoo. And then I put we'll make it, let's just say theoretically it's balanced with this. All I care about are these 2 guys right there, are these. Don't care about water. Why don't I care about water? What's water in this scenario when with neutralizations? Water is always a liquid at this point. Do we care about liquids? No. So in any of the equations I'm going to draw, I'm going to cross water out immediately because it's theoretically a liquid at this point. I don't care about it. Make sense? Okay. So I have that. I got to go to figure out how many grams. Now, this is going back to 113. It's just stoichiometry, right? 0.5 moles per liter, right? Boom. Now, how do I get rid of the liters? I have 76 milliliters of this guy, right? I'm going to get my KOH. So I take the concentration of that, right, which is moles over liters. It's molarity, right? So how do I get rid of the liters and get to moles so I can do a molar ratio? How do I do that? I'm going to use that, 76 milliliters. What's 76 milliliters into liters? Anyone know? 0.0076. Correct? Did I do it correctly? 1, 2, 3. There is only 1 0. You're correct. Boom. Okay. Multiply those 2 numbers together. When I calculate, I got 0.114 moles. So is that what you guys got? Might be off by a factor of 10. I was using a dollar store calculator, so because my sister stole my graphing calculator for her test, so calculations might need exact. So you guys got 0.114? Cool, 0.114, got it. Okay, that's moles of H2SO4, right? But do I want moles of H2SO4 or do I want moles of KOH? KOH, right? How do I go from one part to another part? There's a thing called a molar ratio, right? So for every one of these I neutralize, right, I need to use 2 moles of KOH, right? So 2 moles of KOH. Well, these are touchscreens. I don't like them. Over 1 mole of H2SO4. They make me write like I'm kindergarten or I'm completely drunk. This is great. I swear I'm not either one. That's another lab professor. H2SO4. Cancel, cancel. Okay, so 0.114 times 2 gives you what? 0.228 moles, right? Then I have, you're already given molar mass, so times that by 56.11, and you'll get what? 12.8. The answer for 1 is C. Does that make sense what I did? Yes or no? Because that's the amount, that's the moles of H2SO4 I have, right? And I'm trying to figure out how many grams of KOH it would take to neutralize that, right? And since that is a diprotic acid, right, it's going to take twice the amount of KOH as it would normally to neutralize H2SO4 because it is a diprotic acid. For most diprotic acids, you're going to use this setup. It's very annoying. That's why diprotic acids are annoying. Also why Langley likes to put those on the quiz and exams, because it's not as easy as M1V1 equals M2V2. You can't do those for diprotics. Yeah, for these 6.11, yes. My handwriting's bad. I'm gonna see if I can readjust the camera. Yes. The reason I did that because it wants it in grams. That's how I get to grams. Is this making some sense, guys? Okay. Going to delete it now. Everyone good with that? Cool. Clear docs. Okay. Now, we got to talk about this thing right here. Who was at class today or this week? Have you guys talked about this equation yet? What's the equation called? Hesserson-Hasselbalch equation. Welcome to your new best friend. This is how you find the pH of buffers. Now, a buffer is what, guys? Resist the change in pH. But what is a buffer? It has to have 2 components. A weak acid and its HA is what? Weak acid. And an A minus, its conjugate base. So you're going to use the Hesserson-Hasselbalch equation if you have a weak acid and its conjugate base left. Does that make sense? Because normally Ka, we use Ka, right, squared, Ha, when we only had the acid left over, right? But now in these upcoming questions, we're going to have the conjugate base left over. We can't forget about that guy. That guy matters somewhat. Does that make sense? Okay. So the following refers to 1 liter solution that has HF and NaF. What is the pH of the solution? Well, HF, is that a weak or strong acid? Weak acid, right? NaF, is that a base of HF? If I added NaOH to this guy, right, I would get NaF, correct? So that is a weak acid and its conjugate base. Does that make sense? Basically, if you see the thing attached to a hydrogen, right, usually one of the negative charge molecules, is attached to one of the group 1 or 2 metals, most likely that's going to be the conjugate base, the conjugate acid. Does that make sense? Okay. So I have concentration of a weak acid and its conjugate base. All right? What's that mean? I have a buffer. To use a buffer, I need to use Hesse-Hasselbalch equation. Now, the only thing you guys might not know about yet is pKa. So anytime you see lowercase p, that just means negative log. So pKa is what? The negative log of Ka, right? So take the negative log of this Ka value, and what do you guys get? 3.14. Yeah, pi, right? Plus the log of A over HA. Now, please always put A over HA. You're guys going to mess up the first couple times to do this. But it's always a conjugate base of the conjugate acid. There's a reason for this. We'll talk about that later on, why it's like this, right? But A over HA. So you're going to put 0.37 over 0.25. What do you guys get when you do that? 0.17. Okay. And then take the log of that. I think you may 0.37 divided by 0.25. I got something different when you do 0.37 divided by 0.25. I got 1.14. You guys calculate that correctly? No, I'm just talking about this in general right here. Okay. Again, I'm using a dollar store calculator, so I had to stop at the store today before I came here. That's why I was a little late. So to do this, I need to do everything by one hand, step by step. 1.14, get log of that, right? Plus 3.14, you're going to get, when you basically plug all this together, you'll get 3.31. That's the pH of our buffer. Does that make sense? Some of you guys look confused. If you have questions, please ask. Same thing with you too, Zoomies. You're here to help. You're here to help too. If you have questions, please ask. We're all good on this? .14 is the pKa, right? So I just took the negative log of Ka. So negative log of Ka is equal to 3.14. That's where I got that from. Okay. Everyone else got any more questions for me? Okay. We're always going to come back to this guy right here. Okay. So which of the following statements correctly describes a typical titration curve for a strong acid, strong base? So I'll draw it for you guys. So strong acid. Okay. So beginning pH is very low. Is that true for a strong acid? Yes or no? Ding ding, that's correct. The pH of change is slow until the equivalence point. Does it jump up right here? Yes or no? Then that is true, right? It doesn't change dramatically until after the equivalence point. Those of you who did acid base 2 in lab, right? It took forever for the pH to jump, correct? That's because it doesn't jump until you get to the equivalence point. Okay. At the equivalence point, pH changes by a large value. True or false? Did the pH go up by a lot right here? Okay. Beyond the equivalence point, it plateaus. Not really. It still goes on for a bit, right? So that's actually wrong. 4 is wrong. At the equivalence point, the pH would be less than 3.5. So I'm gonna let you guys know this. When a strong acid, strong base react, right, what type of solution do they form? When a strong acid, strong bases react, what type of solution forms? Neutral. So what's the pH of the equivalence point gonna be? Roughly near 7, right? So equivalence point's gonna be neutral or around neutral. Is 3.5 neutral or around neutral? No, it's very acidic, right? So that's wrong. So 1, 2, and 3. Which one is 1, 2, and 3? E. Does that make sense? Okay. What's up? So it doesn't really plateau, right? Because it technically still goes up and over, right? But what 4 is saying, it does look like it plateaus, correct? But 4 is saying immediately, basically after it plateaus straight up. It doesn't, it curves a little bit more. Does that make sense? Because a plateau means it literally just stops and just continues onwards after the equivalence point, which the equivalence point is, so those of you who don't know how to figure out the equivalence point graphically, here's how you do it. It's not the best. Use derivative methods. You draw a straight line, connect the two, draw a middle, right? So here's equivalence point. Does it plateau right there or no? It goes up, then plateaus. So that's why 4 is wrong. If it said increased, then plateaued, it would be correct. But it doesn't just plateau after the equivalence point. Does that make sense? Okay. Cool. Boom. Moving on. Okay. Number 4. So, a 21 milliliter sample of tartric acid is titrated to a phenolphthaleamine endpoint with 20 milliliters of NaOH. Assuming tartric acid is diprotic, what is the molarity? Now, this is the question in which Langley will do this on purpose on the exam. I can tell this right now because he did it to me when I took his class. He does it to all the students. He underlines diprotic for a reason. If it is diprotic, you can't do M1V1 equals M2 V2. It just won't work. You'll get one of these answers, but it won't be right. He does it on purpose because he hates when students try finding an easy method out of things. And I don't feel bad about calling him out because it's true. He will do that. So now we have to figure out a long, convoluted reason for doing this. Okay. So, does anyone know what tartric acid looks like? No, I don't either. So we're going to use the generic, we're just going to use a generic acid, right? Plus NaOH gives us Na2A plus 2 water, and I'll put a 2 here because if I put a 2 in front of the NaOH. But that is the balance equation right there. Right? What's up? Is it hard to see? I can try making it bigger. 1 second. Is that better? Yeah. You guys could have said something. Much better? Yeah. Again, I forgot to put the 2 there. Okay, and then we're gonna swap to, I don't know, let's pick purple. 2, nope. I have 1 of those. Okay, that's the chemical equation I got. You guys are gonna want to start learning how to draw these chemical equations, right? Which comes with practice. So just keep on practicing doing this, right? Because you're gonna want to start doing these because when we actually start doing buffer equations, we're gonna have to start doing ice tables. So it's kind of important understanding what's going on, right? So let's kind of describe it right now. This right there is the diprotic acid. I know that because why? How many hydrogens does it have? 2. A is just going to be the indicator that tells you it's the acid. NaOH, that's given. So Na has a charge of +1, right? So to take 2 of them to bond to the A, right? And I make 2 water. Again, we don't care about water because it's a liquid. Okay. Number 4. Okay. So what is the molarity of the acid? So what am I looking for? Look for the molarity of the acid. That's my acid, right? Molarity of the acid. Look for the acid. Okay. So what is molarity? Big M, moles over liters. Good. So first, what I need to do is I need to convert the thing I have given to me, which is a concentration of one molarity, right, for 20 milliliters. Change 20 milliliters into liters. Divide that by 1,000. What do you guys get? 0.02 liters. Okay. I got 0.02. Is that correct? Cool. And then 1 mole per liter. That's just the concentration of NaOH, right?
Shane,
What's up?
what did you just do?
Okay. You done with your game?
Yeah, I've been done. They surrendered.
Well, that's fun. Okay. So what I'm doing now is I'm trying to get to moles of H2A, the weak acid, right? So I need to get to moles of NaOH first. So we know that molarity is moles over liters, right? So I want to get rid of the liters part, so I use the volume of the NaOH given to me. Does that make sense? So all I did was take 20 milliliters and convert that into 0.02 liters. And I multiplied that guy by 1 mole per 1 liter. Does that make sense so far, Madison?
Yeah, thank you.
Okay. Cool. So what's 0.02 times 1? 0.02 moles of H2A. Nope, not H2A, my bad. NaOH. So, doing the exact same thing. I take 2 moles of that guy to make 1 mole of that guy, right? So we're going to do molar ratio. 2 moles of NaOH. 1 mole of H2A. Cancel. Cancel. So 0.02 divided by 2 gives you what? 0.01 mole. Now, I use its volume, right? So divide the 0.01, change my color right here to red, right? 0.01 divided by its volume, change into liters, of 0.021 moles per liter. Does that make sense? So anytime you do diprotic, and since the word diprotic, you're going to basically do stoichiometry. Does that make sense? It takes longer and it's very annoying. Trust me. Monoprotic, we'll do a couple monoprotics later on. They're so much easier as long as you know what you plug in the right values. 0.48. Okay. Everyone follow along so far? Okay. Good, good, good. Okay. Number 5. Choose the expression that gives the molar concentration of HCl if a solution of that in NaOH. Cool. When I read this, I see strong acid, monoprotic, strong base. Instantly your mind to jump to this. M1 V1 equals M2 V2. Cool. So what am I looking for? I'm looking for the concentration of my acid. you want to make that guy, want to make it M1 or M2? What do you guys want? Want to make the acid M1 or M2? Okay, the acid will be M1 now. So M1 times how many, what's the solution of the acid? There we go, 30. So M1 is going to stick with 30. Then we're going to, let's do, I don't know, let's do teal, right? 0.105, does that come up good? It comes up okay, right? Big M times the base's volume, 24.3. Okay, how do I solve for M1? Which one of these guys looks just like the equation right here? C? And the answer is C. Good job. Does that make sense? What's up? Yep, and it's monoprotic. Yep. Because it's both associated 100%, right? They both associate 100%, then no matter whatever I put in, I'm going to get out. Correct? That's why I do that. What's up? No, the reason being because if this is milliliters, right? So 24.3, right? Milliliters divided by milliliters, they cancel out. So you don't have to. You can if you want everything to be consistent, right? But the units cancel out. So the only thing left over I have is milliliters. Or sorry, the only thing I have left over is molarity. Okay, any more questions? Okay. As soon as you have questions, type in chat or just call out to me. Okay. See, monoprotic much easier, isn't it? So M1V was M2V2. Okay. Number 6 is where stuff starts getting a bit difficult for this chapter. So calculate the pH of a solution that is HF, NaF. HF, strong or weak? NaF, what is that? Conjugate base. What do I have? Which is it's a buffer. A buffer solution, right? So I have this buffer, and I added this guy right here. NaOH. What's NaOH going to attack? The acid or the base? Attack the acid, right? So I'm going to draw this in black. NaOH plus HF will make NaF plus water. But do we care about the water? No. So you just cancel the water out or just forget about it. Okay. Now we're going to do an ice table. So normally with initial, we've always done before, right? There's nothing there. We already have a buffer solution, right? So we already have stuff in the buffer. And I had 2 big M's of that guy and 0.439 big M's of that guy, right? That making sense? You guys see that or not? It says in the equation, here and here. And then I added 1 mole, not 1 mole, so 1 molarity of NaOH. Okay, so the NaOH is going to attack the acid. So if I subtract 1 from here, I subtract 1 from here. Is that making sense? You're going to subtract from the acid's going to attack the base. The base is going to attack the acid. This will make more sense later on, trust me. Your way of the way they taught you makes sense too, but it gets really complicated once we're given the same buffer solution and we're told to manipulate it with an acid and a base. Yes. You're going to do that. Okay. You choose the smallest one on the reactant side, or you just know that the acid and base are going to neutralize, try neutralizing each other, right? And I have more acid or more base? Which one do I have more of? Acid. Did my buffer survive? Do I still have a conjugate acid, sorry, a weak acid and a conjugate base? Do I still have HF and NAF? Yes or no? I still have them. My buffer survived. It means it can do its job a bit more, right? There's scenario, we're gonna learn scenarios, especially, I'm gonna kind of skip down real quick to show you guys what I'm talking about. So 1 second, skip down right here. Where questions 40 through 41 is scenarios of buffers where buffers will either survive, it will break, and the acid will kind of neutralize it and kill it. You'll see when it gets there. Okay, and we are right about. Whatever, close enough. Cool. Let's actually zoom down a little bit. There we go. So I subtract from the product side, add to the reactant side, right? So now I'm going to add. Oop, I closed something by accident. So it'd be 1.439 concentration. Does that make sense? How I got this? Because if one concentration molarity reacted over here, I'm going to make 1 molarity on my product side. Does it make sense? Whatever I lose on my reactant side, I have to make on the product side. The equation has to be balanced. Okay, I still have my weak acid, my conjugate base. I'm asked to find the pH of the solution. What equation do I use? Yep, use the Hasselbalch equation. So pH is equal to pKa plus log of A minus over HA, the concentration of A minus over HA. Okay. So the pKa value, or the negative log of this Ka, bring that down here, right? I'll plug the value in because it's going to confuse students. So 7.2 times 10 to the negative 4th. That got me, again, 3.14 plus the log of A over HA, so 1.439 over 1. Which then got me the log of 1.439, I got 0.16. 0.16 plus 3.14 gives me 3.30. Does that make sense? If it doesn't make sense, we need to just keep going. We need to go over this because this is the heavily tested part on chapter 17. This is the first biggest concept we're going over. Does this make sense to you guys? Yes or no? No?
Not entirely.
Okay. What part is confusing to you guys? What step?
How did you get the 8.2 again for your log?
The 8.2?
Is that 8 or is that a 7? Oh, it's a 7.
It's a 7.
That
Right
makes more sense. Okay.
Sorry, my handwriting's awful.
No, it's okay.
Again, I'm not drunk or a third grader. It's just this thing has to be recalibrated. I'm not going to spend time to do that right now. Okay. You, what's confusing you? Which part? So type in, do you have a calculator with you? No? You have a calculator, right? There you go. Type in the log of 1.439. What'd you get? 158, round that up to 0.16, right? Do you see that? That's how I got the 0.16. That's how I got that. Everyone else got any questions on this? What's up? Yep, conjugate base over weak acid. Yep, always conjugate base for weak acid. Yep. Okay. Anyone else got any questions? Zoomies, anyone else?
Just because this takes such a long time, is not.
Nope, he is. This will be on the test, the exam, and the quiz. So this, well, yes, what's up? You had the 3.14 plus the 16, yes. So this guy right here becomes a 16, right? And we just add them together. That's why I got the 3.3. Yes. It does take a long time. It takes a long time because you guys are new to this phenomenon, right? Once you actually do it, it doesn't take very long. You'll see later on. So it does take more time than normal, but it takes less time than other questions. And it's basically, I can almost guarantee that the test will be just like questions 40 through 44, because again, it's a bunch of buffer scenarios depending on different things. Yeah, he tells you not to. You can. Yeah. Only for strong acids, weak bases. The reason they tell you not to is because students tend to try doing M1V1 for diprotic acids. You can't do for diprotic acids. Only strong acids, strong bases. You could use the Hasselbalch equation. That's one way of doing it. Or you could calculate a diprotic acid, where you have to draw the equation and then do stoichiometry. But if you do it that way, it basically ends up being M1V1 with M2V2. No matter what, it ends up being just like it, right? It just only works for monoprotic strong acids with strong bases. Okay. Anyone's got any questions? Okay. Okay. So again, what makes a buffer? Oh, I messed up one. Oh, sorry, 7, there we go. The pH of the following solution, which is HNO2. What is that guy? Strong or weak? Okay, strong with that guy, right? So I have the solution of this plus NaNO2. Yes, conjugate base. So it's a strong acid and it's conjugate base. Is this a buffer really? Yes or no? No, it's not a buffer, right? We can make it a buffer if we add stuff to it, right? But we're not doing that question right now. So what are the equations? What we do will not change the pH. So
Wait, isn't HNO3 the strong acid?
oh, you're right. Yes, you are correct. I messed up. You're right. So it is a weak acid. It is a weak acid. It's conjugate base. Thank you. Thank you. Yep. So it is a weak acid. My bad, guys. Okay. It is a buffer. And buffers, like everything, right, are going to be. Oh, I'm drawing with lines. Don't do that. Draw with letters. There you go. Oops. Our buffers are going to be in equilibrium. This is important because I can change Le Chatelier's principle and I can change what it's going to be. The reason I put an X there, right, is because that's going to be what I'm adding to the equation, right? Okay. So let's say let's do the easy ones real quick. C, hydrochloric acid. If I add an acid to something, is that going to change the pH? Even a buffer is going to have a change in pH, right? 7 saying no change in pH whatsoever. So that's going to change pH. Okay. What about NH4NO3? Ammonium nitrite. Ammonia is an acid. Even if it's a weak acid, it's still going to change the pH a little bit, right? HNO2. It's a weak acid, still going to change it, right? Acid, acid, acid. Those are wrong. Okay. Here's where it gets very, very interesting. Adding A will also change the acidity because KNO2 is just like what other conjugate base up here? The sodium. Let's not do yellow. Yellow's a bad color to see. Let's do blue. Just like the sodium, right? It's also group 1 metal with a nitride on it. If I add that to the solution, it's going to act just like sodium, right? So sodium's going to technically increase. If sodium over there increases, what happens to, I make more of this, right? Deschatte's principle. I increase that side, so it has to make more reactant to compensate, correct? Did I just make more acid because of that? Is that changing the pH? Yes. A is wrong. B doesn't do anything because this is NO3, this is NO2. Different. They're not the same ion. It won't do anything to this equation. Does that make sense? Not a common ion. Okay. Clear, John. Okay. So, which of the following is an inefficient buffer? Okay, again, a buffer is a what? Or a weak base plus a conjugate acid. I keep saying this, guys, because questions like 8 will pop on the test because they love to torment you guys with this, right? So ammonium chloride, NH4Cl, NH3OH. Are any of those guys strong acids, strong bases? No, right? It is a weak acid and its conjugate base, correct? Do you guys see that? This has 4, this has 3, correct? That is a good buffer. Sodium chloride, okay. NaCl plus NaOH. Strong or weak? NaOH.
Strong.
Strong. Is that going to make a buffer?
Nope.
Nope. That's the answer. The rest of them, you guys, I'm not going to do the rest of them because you guys want you guys to practice drawing these things out. But B is the answer because NaOH is already a strong base. Strong bases cannot form buffers. Does that make sense? That's why B is the right answer, because the question is looking for an inefficient buffer. That's why. Does that make sense? Because that is a strong base, not a weak base. Okay. I'll do that one pretty quickly because I want to spend more time on number 9. So this is the first time we're dealing with KSP. So KSP is the product solubility constant. So let's break this word down. What side of the equation is looking at? The product side. K for constant, right? And what's the SP stand for? Solubility. What does solubility mean? How likely is it to dissolve in water, right? Okay. This is going to get a little weird, but trust me. Li3 PO4 plus water. So when I put this thing in water, what are the ions going to be? It's going to break apart, right? Because water likes to break apart ions. I'm going to get 3 lithium, right? Plus 1 PO4, 1 phosphate, right? Does that make sense? Okay. Oh, we go about 4. It's right here. Yeah, the PO4 is that's a polyatomic. That stays together. Okay. The 3 goes there because the 3 is right there. 3 talks to that guy. Okay. Here's where things get weird. Now, Deo Langley might teach you with an S. I don't like using the S variable because it confuses you guys. I'm using the X variable. So what's going to happen is these guys have their own solubility product, right? Every single product is going to have its own solubility product, which is going to be considered an X variable. Lithium, though, with the donate that this has a 3, and it's to the 3rd power because we're dealing with K value, right? PO4 is just a normal X value to the 1st power if you want to do that. These guys are multiplied together. So KSP is equal to 3x cubed times x to the 1st power. What is 3x cubed? What is 3 cubed? What is 3 times 3 times 3?
27.
27x to the 3rd times x is what? 27x to the 4th power is equal to KSP. It gets weird. That's how the best way of explaining it is to do it that way. Break apart the products into their ions and then just multiply them by the x, but keep the coefficient as there and make it the exponent. Why do the exponent? Because remember with K, anytime I have something in front of the number, it also becomes an exponent. It's just following the same K values as before, right? That's how it's going to be done. So, plug in KSP. (3.2 times 10 to the -9th is equal to 27x to the 4th power. Solve for x, because that is the molar solubility, solubility product constant, or the x value. Molar solubility, sorry. So we're going to solve for x. How do you solve for x? What's the first step? So I'm just going to draw this guy over here in a different color. So it's an entirely different step. Let's use different blue. Okay. So 3.2 times 10 to the 9th divided by 27. And then I take that entire thing to the 4th root power. That is what x is going to be. You guys need to start learning how to use the x to like the 4th root power, the 3rd root power on your guys' calculators. Because this will pop up from now on in chemistry. Weird exponent roots of this stuff. Most calculators have something like that. It's right above the caret number. So try finding it.
The answer is 3.3 times 10 to the -3rd.
Yep. You're correct. This is the answer. I'm just waiting for everyone else in the class to solve for it. Yes, A is the answer. That makes sense, guys? What I kind of did? I know it's a bit weird. We'll figure out, so we'll do it a bit more later on.
Can they ask for like what's its most solubility in something else besides water?
Yes, it will. We'll talk about that when it happens. So,
Okay.
But mainly it's an aspect solubility in water 95% of the time. Okay. Making sense? Okay. So, as you guys get your attention, you guys think about this question. Higher KSP means what? What's a higher KSP mean? More soluble or less soluble? What do you guys think? So it's either yes or no. More soluble or less soluble? It's either one or the other. So higher KSP, an increase in KSP is going to mean more soluble. That's going to come important later on too. But higher KSP, more soluble. Because you're going to get some numbers where it's going to be like 3.2 times 10 to the -40th. Is that thing soluble in water? No. Because that's way bigger than that, right? So you're gonna have to do some ranking questions in a little bit. Okay. Hey, number 10, more KSP value. What's up? Of the square root? It depends on your calculator. Every calculator is different. You need to practice on your calculator. Sorry. Usually it's near the caret button, but every calculator is different. If you go to YouTube and just Google it, look up how to use a calculator. What's up? Yes. That works too. Okay, a saturated solution of magnesium fluoride has a concentration of that. What is the KSP value? Right? This right here is the X value. So we're going to plug that into the X and solve for KSP. Does that make sense? Because that is the molar solubility. Because it's in molarity. That is the X value. No, because it's magnesium fluoride. So magnesium is located in what group? 1, 2, or 3? 2. So magnesium has what charge? Fluorine. Where's it found? It's a halogen, right? Has a -1 charge. So how many fluorines do I need to bond to my magnesium? Right? So let's use black. When magnesium fluoride bonds with water, I'll get Mg plus 2F, right? Which will equal X times 2X squared. Mg just becomes the 1X. 2F becomes the 2X squared. What's up? Yes. Yep, exactly. So you put it in front, and you also take the X. You also make it the exponent. Okay. There's a reason why, but I'm not going to waste your time on why it's like that. Just know it's how you do it for now, right? Because this is the only time we're going to deal with KSPs in Chapter 17. That's it. So there's no reason to keep dwelling on a topic you're only going to see on one quiz and one exam, but barely, right? I think it's a waste of time to know exactly why this works instead of just knowing how to do it.
Shane, I have a quick question.
What's up?
So every time it's coming, the 2 in the coefficient of X and the 2 in the exponent is coming off the coefficient of F, right?
Yep, exactly.
It goes in both spots just
Yep.
because for now.
Yep. If that was a 3, it would be 3x cubed. If it was a 4, it'd be 4x to the 4th.
Okay, thank you.
Yep. Whatever this coefficient right here is, pops in front and also becomes the exponent.
Gotcha.
So, yep. Good. Okay. So X times what is 2 squared? What's that guy equal? X times 4x squared. 4x cubed. 4x cubed is equal to KSP. This was X, I told you, right? Plug that in for X. Which one of these guys looks just like this, but with X plugged in? C. So C is the right answer. That's all it's asking for. Does that make sense? You don't have to solve it. You just got to figure out what it's asking for. So it's gonna be solved. It's so you're seeing a progression, right? We're number 11. We're gonna solve for it now, right? Okay. Okay. 11's a bit confusing. I don't like it. Okay. So we have PB NO3 to the 2 power, right? That's going to equal KSP. So let's break this guy up. We have PB, concentration of PB, the concentration of 2NO3 squared. So you'll get 4x to the third. Is making sense so far? 4x to the third. And that's going to equal KSP. Solve. This is the ones I didn't solve because my calculator, again, it's a dollar store one, doesn't have the right components to compute some of these questions. So you guys can tell me what the answer is.
Shane, how are you getting 4x3?
Okay. So how many lead atoms do I have in that thing, Madison?
1.
So I just make that a concentration of 1. How many nitrites do I have here?
2.
2. So I make nitrite NO3. I put the 2 in front and make the 2 the exponent, right? And then I just change both these values to the x. So that's 2x squared times x. Does that make sense?
Yeah.
Okay, that's how I get 4x to the cubed.
Oh, and then you just, that squared went on to the 2 to make it 4.
Yep. Okay. What do you guys get? What? You're solving for x. So you're plugging in 7.1 times 10 to the negative 9th, solve for x. So you can divide this by 4 and take the cubed roots. That's what you're gonna do. So solve for x. What do you guys get for x? 0.0012. Okay. This is one I didn't do because I didn't have time to do it. So we'll say it's A. I don't know if I'm 100% sure. I could check it out real quick. Give me 1 second. Yes, I'm gonna open up. Okay. Just check real quick, be sure. Question number 11. Yep. Yep. That makes sense to everyone?
No, I got a different answer.
You got a different answer? What'd you get?
I got 0.0012. So I'm a
Also, that's also what I got.
So you got 0.23.
0.00121. So
This could be a mathematical issue on Langley's part, but it's the closest one to it. You'll see when you're dealing with numbers this small, miscalculations happen very easily depending on how you guys round. So just pick the closest one to it, which is this guy, which is A.
okay.
That's why you guys should always be showing your work on quizzes and exams in case there is a miskey or there's a typo or miscalculation. You guys show the correct work for what was given to you. You should get points back. Yep. Yep. See? You guys do that. Guess what's going to happen on the lab exams? Last year, I believe for 115, there was like 10 issues. So, yeah. The entire buffer and solubility lab, Langley messed up like the entire key. So, be careful. It happens. Math is not everyone's forte. Okay. Does 11 make sense to you guys? Okay. So, whoever asked that if it's an acid more soluble besides something in water, guess what? Is it more soluble in H+? So is it more soluble in an acid? Right? So, let's find out. We're going to add basically an acid to each of these guys. If I add hydrogen to this guy, what do I get? What's this? Does that want to exist? Does strong acids want to exist? No, they dissociate 100%, right? So I made a strong acid. So if I add an acid to this, if I add acid to salts, it won't react, right? It won't dissolve because it's just going to make what? The salt again. Does it make sense? So nothing's going to happen. It's not going to be soluble. Let's draw B out here. Give Ki, right? So HI plus K. Strong acid. So A is wrong, B is wrong. HPO4, what's that? H2PO4, how about that? Strong or weak? Is it weak? Yep, it is weak. Good job. Good. That one's the only candidate so far because it actually will form a weak acid, right? Which means it will be kind of dissolvable. HBr for D. HNO3. C is the only answer because it makes a weak acid. That is why. That's why it's more soluble in an acid solution besides pure water, because it will form a weak acid, which itself is pretty soluble and stuff. What's up?
Are all the strong acids at the same pH?
No.
So technically there would be like a more right answer.
Yes. Yes, but it would have to be the Ka value or a pH value, but more than the Ka value. Like hydrochloric acid, it's ranked like 0.12, theoretically speaking. So it's very, 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 very strong.
So if that was on there, you know.
It would, yes, but they're not going to ask that question without giving the Ka value. You won't have to rank acids unless they give you something. You guys are undergraduates. You don't need to know the ranking of acids just yet. You just need to know if it's strong or it's weak. Okay. Okay, moving on. Does 12 make sense to you guys? Okay. 13. So which one's gonna have the lowest molar solubility? So which of the following has the solubility constant K equal to the molar solubility constant? Okay. What this means is, which one's gonna have the smallest X value? All right, because it's a solubility product. Oh, sorry. For molar solubility. Molar solubility. Least solubility. Okay. Let's do red for A. Okay. So, if those things break apart in water, what is formed? I have an M value. I have an X value, right? One of each, right? So it's going to be X times X theoretically, correct? X squared is equal to that. See the square root of that? So you can plug that in if you want to. Not going to be very high, right? Okay. What about B? Let's do, I don't know, purple. M times X, or 2X. 2X. So the associated water, I'll get the concentration of M over the concentration of 2x squared. What's that going to be? That's going to be 4x cubed equal to KSP, right? Basically the same thing as D. Do you guys see that? How B and D pretty much be the exact same thing? So do you think B is going to be the answer? Probably not, because there's two of the exact same ones. Hint, hint, wink, wink. If two of the same things pop up, probably not the right answer. Okay. Let's do blue for C. C is not the right answer. I'm just trying to show you what color I'm using. Okay. So blue is going to be M times 3x. Concentration of M, concentration of 3x cubed is equal to 27x to the 4th power. Okay. And then let's do dark green for this guy. This is going to be 2m times 3x. So that's going to be 2m squared times 3x cubed. So 4 to the x to the 2nd power times 27x to the 3rd power. That's going to be 4 times 27 is what? Like something, right? 108?
Yeah.
108x to the 7th power. Woohoo! Which one of these things is the smallest? Yeah, 5th power, my bad. It's been a long day, guys. It's almost been 12 hours of working. So I do apologize. If I make mistakes, I do apologize. Yes, it's the 5th power. Okay, which one of those do you think is the smallest? I did the work for you already. The answer is A. 13A is going to give the smallest x value. You can plug all the work in and do it. It's going to give the smallest one. The reason being, you're going to start multiplying by gigantic numbers, right? Even if you take ridiculously to the 5th power, the 4th to the 3rd power, multiplying things about 427 to 108th is pretty big. Also, when these numbers are so small, taking the square root actually makes them, taking anything above a square root actually makes the numbers bigger. So you're just getting bigger and bigger x values. That making sense? What's up? Because how many of each do I have? One of each, right? I have 1m and 1x, right? So if I draw that out, concentration of M times the concentration of X, both basically technically the 1st power, right? It's going to be X times X or X squared. Does that make sense or no? I just simplified it. I skipped this step. We just did for the last 4 problems, so I thought you guys would understand that. So, for example, here I just converted that to this guy right away. But I'm treating the m like its own, like an exponent. Yes, I am including yes. That's how I got to the 3rd, right there, and to the 4th, and to the 5th. Okay. This making sense to everyone? I think KSP is an easier concept than buffers will be. You'll see why. Okay. Zoomies, got questions for me?
Shane, is it E or A?
Oh, it should be A. Sorry. Whoops, eraser. The answer is A.
Thank you.
A. A. Okay. Moving on. Woohoo! 14. Conceptual questions. Which of the following, when added together, will develop a buffer? So it's step by step. HCl4, strong or weak acid? HCl4 though, is it strong? Is it?
Was it HClO3 or HClO4? I don't remember.
HClO4.
Hmm.
Okay. L4 will change it. I think HCl3 is a strong acid. HCl4 is a weak acid. It's also a strong acid? Okay. Well, that's gonna be weird because that's one of the answers. You'll see why in a little bit. Okay. The reason being that's going to be a buffer is because I'm pretty sure that is a weak acid, guys. Let's find out. HClO4, strong or weak? Oh, you're right. It is a strong acid. Well, that's weird because that's one of the answers. Interesting. I forgot why I picked that. Huh. Okay, we'll come back to that one later then. Okay, I know that HPO3 though, that is a strong acid, correct? HPO3, H3PO4? Weak? That one. Okay. Wow. Very long day for me. Okay. Equal volumes, the two solutions are mixed. So that is a weak acid in its conjugate base. That is true. Ah, here we go. This is why. Okay. Sorry, guys. I got this question mixed up with another one. Two is not the right answer. This being because that right there, you were correct. It is a weak acid. That right there is technically also the conjugate base, but does it still have hydrogens left over to donate? So can it also be an acid? So it also could be an acid depending on the solution I add it to. Correct? Is that a buffer then? No, not a buffer. 3, KOH is a what? Strong base, HCN, weak acid. This will form water plus what? KCN, potassium cyanide. Now, here's where things get a bit tricky, guys. Which one, is there more of the base or more of the acid? More base or more acid? There's more base? That number is bigger than that number? If I give you 50 cents, you'll give me $1? Yeah? Okay. No. So the base is going to run out first, right? So theoretically, going to happen, this guy's going to run out first, leaving this and this behind, correct? So that's going to form, yay, a buffer. Number one's technically right. Technically right, yes. Okay. 4 is wrong because the exact opposite reason 3 is right. Yeah, they're flipped. So. Wait, this question's making no sense. I think there's a typo in this question somewhere. I think they try to beat Chegg, but the key wasn't changed correctly. Give me a second. Yeah, but it can't be E though. 1, 3, and 5 is one of them. Yep, they changed this answer from the last time I did it. So I'm using the answers I got from the last one because the one you sent me, Athena, wouldn't open up my computer for some reason. So I'm using last semester's. They changed it. Give me a hot second. It's the only one they changed. That is going to be wrong. This one right here is going to be wrong. 3 is correct. Okay. Which one is this one? This is 14. Ooh. Copy. Sorry about this, guys. No, I don't see one. Oh, they changed stuff. Okay. Aha, okay. So, here we go. 1. Okay, I have misspoken. This and this. So the answer is C. I'm guessing, I don't like that 2 is one of the answers, but it's the only one that gives me 3 and 5. Okay.
They said that in my lecture class, they said that the only conjugate base that is still considered an acid is HSO4.
HSO4?
Mm-hmm.
Okay, then that's why then, okay. That's that one, I forgot that obscure rule. Okay. So that's why the answer is 2, 3, and 5. Okay. What's up?
For 3, so HCN is weak acid, right?
Yes, but it's strong, there's more of it than the base, right? So the base won't neutralize it completely. There's still gonna be base left over, right? There's still gonna be some HCN left over with its conjugate, with its conjugate base. Even though it's a strong base, yes. It's not saying both, it's saying if I add these 2 things together, will it form a buffer. Not if these 2 things alone make a buffer. If these 2 solutions and what's falling end is a buffer solution, when equal volumes are mixed together. So when those 2 are mixed, they form a buffer. That's what the question's asking for. Yeah, it's what makes a buffer. Okay. Sorry about that, guys. The answer, it's C. They changed the numbers around from last semesters. That's why I confused those. I do apologize. Okay. Everything else though is exactly the same except that one question. Don't know why they did that. What is the pH of a solution containing blah, blah, blah? Okay. So, $15. Which one of those is the acid? Which one of those is the base? Which one of those has an extra hydrogen to donate? Okay. Issue is, Hesterson-Hasselbalch equation is pH is equal to pKa plus log of A minus over HA, right? Am I giving Ka? and KB. So there are two ways to do this equation. If you guys are confident in your calculator skills, KW is KA times KB, right? KA is equal to KW divided by KB. You can solve for K that way, plug K in, boom, you're done. That's if you're confident in your calculator skills. If you're not confident in your calculator skills, here's the other way to solve for this. Since I have KB, all I'm doing is making POH instead. So POH equals KB plus log of, theoretically, B minus over HB, which is the same thing as this. Same thing pretty much. It's 0.4 over 0.25. It's basically the same thing. But instead of getting pH, I get POH. And then remember, pH is equal to 14 minus POH. That's the two ways to do this equation. It's just how confident you are in your calculating skills. Because if you do it this way, you need to put parentheses between the 1 point times 10 to the negative 14th. Parentheses have to be around that, and you have to put parentheses around the 1.1 times 10 to the negative 8th.
So if you were to take the KB plus the log B minus over H, you would just subtract by 14.
Yep, the same answer. Or close enough to the same answer where you guys can pick it. Yes, A is equal to, sorry, my bad. Right, I mistyped this one. Oh, my bad. Okay. Normally, yes, this is the HA and this is the KB. But when doing with POH, this way you flip them around, in which this becomes the B and this becomes the A. You also flip those around. I forgot to mention about that. Why? It's just because that's how the equation works. Because you're not doing the PO, you're doing the POH to the pH. They're kind of opposites of each other. That's why. Because what went up here for the last guy was the conjugate base, right? If I'm solving for the base goes on the bottom, the acid goes up top. Because I'm solving, if you do this way, you have to flip it because POH and pH are the opposites of each other. That's why you flip the numbers for that. Am I making some sense or no?
Would you get 9.09 if you're finding Ka?
I don't know. I didn't solve for Ka. Again, I'm using a new calculator from the dollar store. I'm not gonna trust it using the complicated method. So, if I had a graphing calculator, a calculator I was used to using, I would. Again, I just bought this. I just bought this today, and it's already dead in battery. So, yay, dollar store.
What did you see was the A minus? The HA?
So you're gonna plug in 0.4 divided by 0.25. Yeah, D. I got B. Okay, so we have different answers. Let me see your graphing calculator. So that's PK, right? And I got the
Oh, yes. Yeah, that's good.
and then do what's up? Yeah, what? B? B or D? Yeah. Conjugate acid over the base. Okay. Whoopsie daisy. In my calculations, I did my own. I forgot to minus the 14. That's my bad. What's up? Yes, it is C. Okay. So this is my bad. I got to this part and forgot to minus 14. So you will get C as the answer, not B. So the answer is C. Sorry about that.
Shane,
What?
for the, you know how you have B, you changed it to B minus over HB?
Yeah.
Why'd you plug them in the way that you did? Why'd you flip them?
Because it's going to be, the way the equation works, it's just the conjugate acid over the base. Right? Oh. Yeah.
Because if you plug it in a different way, it gives you the other answers too. That's why I'm just making sure, like, if it's that way or the other way.
Oh. Again, don't do homework at 3 o'clock in the morning, guys. I do apologize. Probably redo this whole video. NH2OH is a base. That is a base. This is a conjugate acid of the base. All right? I also have a weak acid, a weak base and it's conjugate acid. So if you do the POH of the PKB plus the log of 0.4 over 0.25, you will get the answer. That will give you the 8.16 for POH. And then you'll solve for pH is equal to 8.16 minus 14. I messed up. I do apologize. This right here is a weak base, not a conjugate, conjugate base.
So for that one, you did put the 0.4 and the 0.25.
Yeah. So the answer is C.
If you maybe decide to go with the H, it's gonna be A, you would just flip it again.
Okay. Moving on. It's the conjugate acid over the base. It's going to be this guy over this guy. 0.4 over 0.25. Okay. The answer is C. Or the PKB, you mean? PKB is 7.95. You can't be negative. The negative log of 1.1 times 10 to the 8th can't be negative. If KB or K negative, so you probably entered something in wrong. This is what equals KB. These two things equal each other. Okay. Okay, moving on, because we have to move on. Okay, 16. A buffer solution containing hydrocyanic acid and potassium cyanide. And then I add KOH to it. What is the pH after the KOH is added? So I'm adding what to my buffer? Which is a base, right? So KOH plus. Which one's my acid? Which one's my base? This is my acid. This is my base. This one I'm sure of. KCN plus water. Cancel. I will get some an ice table because you always do ice for buffer. Now, here's an issue with this. If you notice something, the buffer is in a different concentration and a different volume, right? Than my base. Do you guys see that? The hydrogen cyanide and potassium cyanide, they're both at one molarity at 150 milliliters, right? This KOH is that at that, 0.12 at 30. What this means is we need to convert them all to the similar units. Guess what that is? Moles. Convert everything to moles. So 150 milliliters to liters gives me what? Is it 0.15? Liters, cool. That times 0.1 gives you what? That's concentration. Gives you what? .15. Okay, well, I asked you guys. I can't use my calculator, it's dead. Sure. I'll use a graphing one. That way I can use these real quick. Okay. Sure. More interested in the actual graphing part than the actual little part. I'm back. Okay. So 0.15 times 0.1 gives you this then, right? 0.015 moles. Correct? Yeah. 0.015 moles on that side too, because they're at the same volume with the same concentration. Does that make sense? Why they would be the same? Okay. Now in deep blue, what's up?
Why is it 0.015?
So I need to convert them to moles, right? So the volume was 0.5 liters, right? Then the concentration is 0.1 moles per liter. So if I multiply both by liters, I'll get that. That's why. You're good. Whoops. Not yet. We will at the end. We'll make them the same at the end. Don't worry. You'll see what happens. Okay. So deep blue. So 30 milliliters to liters gives you 0.03 liters times 0.12 moles per liter times 0.12. And I got 0.0036. Everyone following along so far? Moles. Okay. The acid and base are going to react with each other. 0.0036 minus 0.0036. I lose reactants but gain products. This crosses out. Right here, I'll get 0.0114. And over here, I'll do in pink now because it's a separate thing. I'll get, ooh. .0186. Cool. They were both in moles, correct? If you go look at Hessian-Hausbach's equation, pH is equal to pKa plus the log of the concentration of A minus over the concentration of HA. So they are in moles now. I need to turn them into concentration. So I need to divide by a volume. The volume I'm going to divide by is the combined volume of the buffer solution plus whatever I added, right? Because it's going to change the concentration of it, theoretically speaking. So I'm going to take both of my new values and divide by these two guys added up to each other.
Do we convert that to liters or keep it milliliters?
You want to keep it liters.
You add the liters together?
Yep, we're going to add the liters together. Okay. So 0.0114 divided by the combined liters, it's going to be these two things added together, 0.18 liters. So, I don't know, let's pick a different color for everything. Let's do this guy, 0.011, oh, shoot. I know I'm going all over the place, I understand. Is this how the problem works? That's why I'm trying to do different colors. 0.18 liters will give you 0.063. Big M. Let's do black for him. 0.0186 divided by 0.18. 0.0186 divided by 0.18. And I got 0.103. We're going to plug both of these values then into the respective things. So the negative log of 6.2 times 10 to the negative 10th is 9.20. Round up, it's 0.211 plus the log of 0.103 divided by 0.063. I got plus 0.21. These things add together give you what? The answer is E. Is that making sense? Yes or no? What's up? Okay. I added the liters together. The reason we need to do that because technically we changed the volume of the entire solution, right? Because I had some stuff in there and then I added the base to it, which is then change the volume. Changing the volume will also change the concentration theoretically, right? So I added the volumes up, which I did before was 0.15 added up to 0.03. So I take my HA, my weak acid, and my conjugate base, divide both of those by 0.18, you should get respectively 0.063 for the acid and 0.103 for the conjugate base. Plug those into the big equation, and you should get E. You guys doing? You guys get that or no? Okay. Zoomies, how you doing? What's up? Okay, that's pKa, right? So what's pKa? What's that? What's the P mean? Okay, I'm going to delete everything real quick. Okay, pKa is the negative log of Ka. So I see the negative log of that guy, and you should get 9.21 or 9.2078 or something like that, which is rounding up 9.21. Does that make sense? Okay. Any other questions? Zoomies? Okay. Anyone else? The answer is going to be E. Whoops. E. Is that what you got? Okay. Huh? You got C? So I didn't do this part yet because someone was lost on how I got the 9.21. If you do this, you get 0.21. 9.21 times 0.21, or not times, added by 0.21, you'll get 9.42. Does that make sense? Okay. Going down to 17. You notice buffers tend to pop up a lot. Hey, look at this. Potassium acetate and acetic acid. So, Dave's probably gonna get mad at me for telling you guys this, but you can use the M1V1 to M1V1 is M2V2 on this guy because acetic acid is monoprotic, and you're given that. Wait, 17? Never mind, don't ignore me. I misread my own key. My bad. It's a buffer. Never mind, it's a buffer, right? So means we're going to use this guy instead. Concentration of A minus over HA. Now, if you notice something, my acid has what volume, what concentration? So if I divide them, even if I change them, if I divide it by each other, what am I going to get? What's the log of 1? So what does pH equal here? pH is going to equal to pKa. So if you take pKa, which is the negative log of 1.76 times 10 to the negative fifth, right? You'll get the answer, which is E again. That makes sense? Okay. That's why it's nice when the buffer has equal parts weak acid, conjugate base, or weak base, conjugate acid. Okay. So I have a buffer here, and I know that because why? HF, strong or weak? Weak. (17) was E. It's just going to be pH is equal to pKa. Yep. Okay. 18. Okay. So a buffer. Boom, boom. Okay. So I have an acid and I have a base, correct? If I add a base to my buffer, this guy right here is going to react to which one? Which one is this guy to react with? HF or KF? Potassium ions react. So this, what one is saying it reacts with this guy. Is that true? No. That's why that one's wrong. Okay. 2, if small amount of if NaOH is added, the pH will increase. If I add a base, will the pH go up? If HNO3 is added, hydrogen ions react with the fluoride ions. So that's an acid, right? HNO3 is an acid. Is it going to react with the acid or the conjugate base? Is reacting with the hydrogen ions with the fluoride ions, right? So is that going to be true?
Is it asking if the hydrogen ion of the HNO3 would react with fluoride?
Hydrogen ions react with fluoride ions. No, it's saying is this guy's going to react with this, right? It's saying it's react to the base. That's what that one is saying. It doesn't make any sense, right? But if you think about it, when this guy is HNO3 strong or weak? HNO3 strong or weak? Strong. So it dissociates 100%, right? So all I have is H ions. That's going to react with the fluoride ions in the KF. Correct? Does that make sense? Okay. That is true.
Even if it was like let's say it was a weak acid, would it still do the same thing?
Yep.
Okay.
Oh no, they changed one again. Okay. If KF is added, pH will decrease. HF plus an unknown thing is in equilibrium with KF. If KF goes up, it's going to make more HF in theory, correct? Correct? So, before we put E as the answer, let's just double check. I'm also going to call it. Hello? Nope. That's fine. Why does my computer not work? Ah, there we go. They're doing question 15. I just want to make sure it's not going to be E because of the asshole move was E. You think it's B, you're saying? 2 and 3?
No, okay, so if you increase KF, then you would make it more basic, but then if you increase HF, then you would make it more acidic, so wouldn't that balance out? And then it wouldn't be a pH.
Okay. Since KF is the base.
Yes, you're correct. That is my bad. 4 is not right. It's 2 and 3. Yep, it's 2 and 3. I'm thinking of a different rule that applies here. So ignore this part. It's B 2 and 3. So the answer is going to be B. Okay. Moving on to 19. Okay. So which one will not have a change in pH value? This is just like the one we did before. So let's get rid of the obvious answers. If I add an acid, is I can change pH values. If I add an acid, I can change pH values. If I add an acid, I can change pH values. Is E an acid? That's not going to affect anything because there's no common ions to manipulate. That's why E is the answer. If you add KF, it's going to act just like NaF, and it's going to affect the pH. Make sense? Common ions are going to be a factor here. It's going to affect the thing. Common ions are going to affect the pH. Okay. So, long time ago, probably about, I don't know, an hour and 30 minutes ago, told you about KSP. An increase in KSP means what? An increase in solubility, right? So which one finally has the least solubility? Which one has the smallest KSP value? -17th. So nope, nope, nope. C is the answer. Does that make sense? Because the higher KSP is, the more soluble you are, right? So the one with the lowest KSP is the least soluble in water. Does that make sense? Okay. Okay. What's that? What's that? What's that? Strong base. Hey, I'm adding a strong X to a strong base. What formula can I use? M1V1 equals M2V2. Because I'm adding a strong acid to a strong base. They're both monoprotic, right? So I can do this. So going to make sure I do this correctly. Change. You can keep the things as the same. It's not going to affect anything. What did I do here? Why did I change it to moles? Oh, God. Darn you, Langley. M1V1 will normally work. There is just one issue with this, and Langley manipulate problem in the one way in which it will not work, because he is a meanie. Okay, so instead what we're going to do is we're going to make both of them more, so if you notice, do apologize for that. Langley just keeps getting in my way of doing the easy formulas. If you notice, are they in the same concentration, at the same volume? So we gotta make them equal each other somehow. So what can I make, what's a similar unit they can both be in? Moles. Change them both to moles. So I'm gonna use red for the acid, and I'm gonna use deep blue for the base. Let's do the acid first. 200 milliliters into liters, so 200 divided by 1,000, 0.2 moles. That is, oh, not moles, sorry, liters. That is multiplied by 0.2 moles over liters. So 0.2 times 0.2 gives you 0.04 moles of the acid. Base, 100 milliliters is going to be 0.1 liters. That times 0.05 concentration over liters. It's 0.5 times 0.05 gives me 0.005. So acid and bases, how do they interact with each other? They don't like each other. They cancel each other out.
Is the blue and the NaOH?
Yep, blue is NaOH. Red is going to be the HCl. 0.04 minus 0.0005. You mix those together, you get a purple color. Woohoo! 0.035 moles. The issue here being is I changed the volume, correct? Because I titrated them. Is that going to change the volume? If I added two things together, yes or no? So if I add the volumes up, 0.3 liters, so 0.035 divided by 0.3 liters, I'll get a concentration for hydrogen to equal 0.117. Now I'm looking for what? pH is equal to what? Negative log of that guy. So the negative log of 0.117, you'll get C, about 0.92, 0.93. That is the pH of the solution? What? I added the liters together to get this guy. What's up? Why didn't I? The reason I didn't do that is because he gave you both volumes. To do M1V1 to M2V2, right? You can't be given both volumes and concentrations. Does that make sense? Yeah, at different concentrations. Why did I subtract the moles from each other? So when acid and base interact, they cancel each other out, right? Because they're going to react to make what? Water and the salts. Do I care about the water or salt here? For strong acids, strong bases? No. That's why I can just cancel, I can just subtract them from each other. That's why I can do that. Does that make sense? So if I have a cup of acid, right? How do you neutralize acid? How do you guys neutralize an acid? You add base. If you add the base, right, you have to add the exact same amount of acid at the same concentration to neutralize it, correct? Here, was the base I added enough to neutralize my acid? Yes or no? Which one's bigger? The red one or the blue one? The red one's my what? So is my acid bigger? Did I neutralize it? So the base neutralized some of the acid, but not all of it, correct? That's why I subtract them from each other, because there's still acid to be left around. Because I want to titrate more, I can titrate more. Does that make sense? This happens when you add an acid to a base on a small scale, basically. A negative log of 0.117? 117.
Shane, I got a question.
What's up?
I feel like this chapter is not easy to understand. Is that just me, or is this actually?
Nope, it's everyone.
Okay.
That's why Langley and Dave have a hard time teaching it, because it's a harder concept to understand, or harder thing to understand.
Okay.
You're not the only one having a hard time grasping it. It takes time to understand. If you just keep doing the exact same, if you keep doing the exact same, like not the exact same, the same type of problems over and over again, you see a pattern forming. That's why I'm also messing up, because this is my favorite one. I know we don't have time. I know that. I'm just telling you the best way to study.
Okay. Thank you.
Okay. You'll start seeing patterns form if you keep looking at the problems. Okay. 22. What of the following is the best describes what will happen when a solution of silver nitrate is slowly added to a saturated solution of silver acetate without changing the volume? So, look at the equation. What do you guys notice about the equation? What's that mean? So if I add silver nitrate, is nitrate in the equation at all? Then I'm not probably looking at that guy. What am I looking at? The silver. Is there one that just has straight silver? Yeah. So if this increases, right, it's going to shift it towards what side? The left or the right? If I increase my products, I have to shift it towards my reactants, right? So it's going to shift it towards the left, not the right. Okay. If you notice something, what's special about my reactants, my left side? So 22 is C, because I'm going to form solid silver acetate will participate. I'm going to form a solid by adding that guy. Does that make sense?
The silver acetate is the AG.
AgNO3 is silver nitrate. This right here is acetate. That's silver acetate. If I add products, Le Chatelier principle says I shift it towards reactants, correct? You guys making sense? You guys took an exam about this about a week ago. So I shift it towards my reactant side, which means I'm going to form more solid or participants. That makes sense? Yes or no? Does the NO3 matter in my equation? No. So it's going to break apart into that, and I'm only going to get silver out of it. That's why I'm ignoring NO3, because it doesn't play a part in the equation. Make sense? It's going to be in the solution, but it's not going to do anything. Okay. Anything else you guys got? Any other questions on this one? Okay. Moving on. Consider solution prepared by dissolving 0.35 of CH3 NH3 Cl methylamine hydrochloride in 1 liter of methylamine. If hydrochloric acid is added to the buffer solution, what happens to the pH? Go up or down? If I add HCl, which HCl is what? An acid or a base? pH will go up or down. So which two ones only stay down? Okay. Oh, slightly, because the HCl reacts with what? Which one of these guys do you think HCl is going to react with? Hint, hint, wink, wink, the one that doesn't have HCl probably. Correct? This guy right here already has been reacted to HCl before. I know that because what's it have on it? It's got 3 hydrogens plus a chlorine. This guy only has 2 hydrogens. Can this guy accept another hydrogen? Yes, we know it for a fact. Because this guy became that guy. Right? You see that? We went from 2 hydrogens to 3 hydrogens. So we know for a fact that guy can accept the hydrogen. Do you know if the other guy can't accept another hydrogen? Yes or no? Are you guys familiar with that chemical? Then don't assume it can. So that's why I say this guy right here is going to react with it, and you're going to form the weak acid. So C is the answer. Does that make sense? You look confused, Kelsey. What's up? Do you understand the decrease part? If I add an acid, pH go up or down? Goes down. That's why pH is going to decrease, right? So I eliminate A, B, and E. Correct? It's between C and D now. Okay. Which one of these guys can accept a hydrogen? The C one, right? Because this guy, they basically are, one's an acid, one's a base, right? One's a conjugate of the other one, right? So this guy already here has already accepted a hydrogen from something, correct? Meaning this guy right here is technically the base. So the acids attack the base to make the weak acid. That's why C is the right answer. Anyone else have any questions with that one? Okay, we're more than halfway done. Woohoo! Don't worry, it speeds up pretty near the end. Okay. What's the solubility of the compounds will not be affected by a change in pH? So, here's what's going to happen. To not be affected by a change in pH, you need to be a neutral solution. Which one of those up there is a neutral solution? Which one of those guys up there, 24, had a strong acid and strong base react with each other? Do you know any strong acids that have an Na in it? Which strong acid has Na in it? Na in it. That's a strong base, right? So is there any strong acids you think of that can do that? Okay, here we have HF, right? And NaOH reacted with each other, correct? So NaOH plus HF, is that a neutral solution? Yes or no? Is this a strong acid? HF, no. That's going to react to pH. It's going to increase cell solubility of it because it's a basic salt solution, right? It's a conjugate base. The answer is C, because HNO3 is a strong acid reacting with KOH, which is a strong base. You will get KNO3, which is a neutral solution. Okay. So you 24. 25. Volume, concentration, volume, no concentration, monoprotic. Guess what we can finally do, guys? M1V1 is M2V2. The reason we can do this is because we weren't given both we weren't given both concentrations, right? So make sure we put it in correctly. Do you want 1 to be the acid or 2 to be the acid? This right here will be the acid then. This will be the base. So 0.175 times 37.5 milliliters is equal to M1 times 25 liters. Divide by 25 milliliters. Cancel milliliters out. Cancel this entire thing out. Oh, not cancel this entire thing out. But cancel that out. So M1 is equal to 0.175 times 37.5 divided by 25. What's the answer? That's what that is. You only do M1V1 because it's a monoprotic acid and you weren't given the second concentration. Okay. This titration curve. Where's the starting point located? Good. It's below 7, right? Which means it's an acid, but it's not near 1, which means it has to be a weak acid. Where does it go all the way up to? Roughly 12, so a strong base. So it is a weak acid reacting with a strong base. Does that make sense? Okay. Whoops. Molar solubility is X. I am solving for KSP. Magnesium fluoride. Mg2F will give me Mg plus 2F, which we break down into concentration of X times the concentration of 2X squared. Everyone got that so far? They do it on purpose. They're trying to do it on purpose. You guys can make connections and stuff. So 2 squared is what? Four x squared times x is 4x cubed is equal to KSP. Plug this in for your X value, and you'll get KSP. (1.7 times 10 to the negative third). That to the third power times 4. What'd you guys get? 6 point what? You got A? Someone say no? You got that? Yep. A, good job. That's the answer. So now I'm solving for molar solubility. Molar solubility is the X value. So what is the X value when dealing with iron oxide? Hydroxide, my bad. I have an iron and I have 3OH cubed. X value times 3x cubed. 27x to the fourth power is equal to 4 times 10 to negative 38. Solve for x, so divide by 27, then take x to the fourth root. What'd you guys get? So it's D or B? D is the right answer. You guys getting that? You got none of them, Matthew?
I got none of them. I got 0.11.
So 4 times 10 to the negative 38 divided by 27. What'd you get?
1 sec. I just put it all together and did it that way.
Do it step by step.
Step by step.
Always do for these equations. If you're not using graphing calculator, do it step by step. Even if you are doing a graphing calculator, probably do step by step. Recommended.
Oh, I did not do it to the 38th. I just did it to the third.
Yep. So the 38 power.
27.
Very small KSP value. In your master's classes, no. The reason being is because you guys can cheat. Yeah, you could calculate that one is A, 2 is B, so on and so forth, and then you can pass a calculator around to your friends, and they can just hit the something and see all the answers. That's why you can use graphing calculators, because there was a giant cheating ring that happened about 5 years ago. So.
Got it now. Thank you.
Yeah. 29. So, had initial pH of 4. Is that strong or weak? In the middle, right? Okay. The equivalence point, right, was 9. So my equivalence point was 9. Is that 9 7? Or is that 9 close to 7? So it can't be a strong acid, strong base, right? So I can already eliminate A and B. So now that pH of 4, is that gonna be a weak acid or a strong acid? Probably a weak acid, so eliminate D. Okay. So if I have a weak acid and I add a strong acid to it, pH go up or down? If I have an acid and I add an acid to an acid, pH goes down. Did pH go down? No, it went up. The answer is E. I have a weak acid and I added a strong base to it. Hint, hint, wink, wink. Because the base overtook the acid. That's why it went above the equivalence point. Okay. Which of the following could be added to create a buffer? So that guy right there, conjugate acid or weak acid? Sorry, conjugate base or weak acid? Conjugate base. So what's that going to react to? An acid or a base? Eliminate C. Good. How many moles do I have? So if I add exactly 0.4 moles of HCl to it, is that gonna break my conjugate base? If I add this number to that number, do they cancel each other out perfectly? Does that break my buffer? Yeah, there's no more conjugate base left over, right? Buffer no work. I want to give a buffer, have a buffer. So it can't be A and it can't be D, it has to be B. Because there's less acid here than my conjugate base, right? So I'll be given a conjugate acid, theoretically speaking, and a conjugate base. So I'll be given a buffer by doing that. Does that make sense? That's how 30 works. Athena, give me a weird look. What's up? Okay. Is that a weak base? Okay, first off, what is that? That right there has NaCHN, right? Is that a base or an acid? It's a base, right? Okay. And I'm trying to get a buffer. So it's a base of some kind, right? So so it's some type of base, and I'm trying to get a buffer. So a buffer is what? A weak acid and conjugate base, or a weak base plus conjugate acid, right? So I'm saying it's a base. Either I can make it a weak base, or I can make it a conjugate base. If I make it the weak base, I have to add a conjugate acid to it, right? If I want to make it a conjugate base, I add a weak acid to it, correct? So looking at the things given to me, what am I adding more of? Adding more acid, right? So when NaCN plus HCl react to each other, right? What do I get? I get HCN plus NaCl, which I don't care about. Care about this guy. That guy right there, is that a strong or weak acid? It's a weak acid, right? So a weak acid and a conjugate base. There you go. I just formed a buffer by adding HCl to that thing. Does that make sense so far? Cool. So I got to figure out how much of the acid I can add and still have a buffer. If I add D, 0.5, is 0.5 greater than my 0.4? So if I add D, I have HCl left over, right? And if you have a strong acid left over, do you care about your weak acid at all? No, because the strong acid overtakes the weak acid because it's so much stronger. Does that make sense? Because HCl has a K value greater than 1, well, HCl will have a Ka value less than 1. So HCl is way more powerful and important than HCN. Does that make sense? But D cannot be the right answer because I have destroyed my conjugate base and made a strong acid, which overtakes my weak acid. Okay. With A, they equal each other, right? They cancel each other out. So if my conjugate base is cancelized by my strong acid, I only have a weak acid left over, right? Does that form a buffer? No, because a buffer is a weak acid and a conjugate base, right? These guys are exactly the same, so they'll cancel each other out. Does that make sense? So all that's left over is B. So if I add less of the strong acid to my conjugate base, I'll make a little bit of a buffer. That's how you approach that question. Does it kind of make sense now? More than last time? More than before? Okay. What is the pH after KOH is added to HCl, HClO? Okay. So I'm adding a base to an acid, right? KOH plus HClO. When those guys react with each other, what is formed is water. Do I care about water? No. Plus KClO. Hey, weak acid, conjugate base means I form what? More buffer. Let's find out if we do. Okay. So, are they at the same concentration at the same volume? So, with being in the same unit, what's a common unit? What? Moles. So, again, I'm going to do blue for my base and red for my acid. So, 20 milliliters is going to equal 120 zeros, 0.02 liters times 0.1 moles per liters, which I just got from here. So 0.02 times 0.1 gives me 0.002 moles. Okay, let's figure out about my weak acid. So 10 milliliters will give me 0.01 liters. 0.0 liters, whoops, about the 1. 1 liters times 0.2 moles per liter is cancel liters out. I got 0.002. Oh no, what happened? Huh? They cancel each other out. So what happens is, do I have a buffer anymore? 0.002 minus 0.002. Cancel, 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 cancel. 0, 0. Oh no. Over here I have plus 0.002 moles. First off, I have moles. Is that useful for anything so far in this in Chem 115? Is moles useful for anything besides this one niche topic? No, we're going to change the volume. So we're going to divide by the total volume. 0.03 liters. And I'll get what? 0.067 concentration. Is that making sense so far? Okay. Now that I have that, I know it's a fun unit, isn't it, guys? So much fun. Well, because he's not asking these questions like this yet. You guys are still learning. You guys just went over it this week, which I don't like how it's due the week you guys started going over stuff like this. So I deleted everything because all I needed now was that I got 0.067 concentration for my KClO. Now, is that the acid at the base? Which is the base? Oh no. Does Ka work for this base? Darn. So now you have to use Kw is equal to Ka times Kb. And there is no other way to get around this one. You have to do it for this equation. So Kb is equal to Kw over Ka. So 1 times 10 to the negative 14th divided by 3 times 10 to the negative 8th value. I got a Kb value of 3.33 times 10 to the negative 7th. Okay, going back to last unit. Ka and Kb equal what? X squared over HB, right? Well, if I solve for X, I'll solve for the OH concentration, right? Which, given the negative log of that number, will give me POH, right? Yeah, it's coming back. I know, it sucks. Find POH. If I find POH, I can find pH, correct? So I'm going to do that. So 3.33 times 10 to the negative 7th is equal to X squared over 0.067. Solve for X squared. 3.33 times 10 to the 7th, I already have that, boom, times 0.067. Take the square root of that number. I get a OH score of 1.5 times 10 to the negative 4th power. The negative log of 1.5 times 10 to the negative 4th is, I don't know yet, give me 1 second. Oops. 3.8. That minus 14 is 10.17 or 10.2. Does that make sense how to get that one? Welcome to the hard part about buffers. That's why you want your buffers to last. It makes the problem really, really easy. If the buffer gets destroyed, it's a pain in the butt to solve for. Okay. What? Is that what you needed? Okay. What's up? I don't know. I don't know. What's a normal quiz like? How many questions are normal quiz? 20? It could be 20 questions. Yep. You'll see what the questions will look like. I keep saying that once we get to 40 through 44 is what the quiz is going to look like, because it's one series of questions all about the exact same thing. You'll see that. You're also going to have some KSP values on it, which do take time, but they're not too bad. It's these buffer ones that take forever, I know. Okay. I mean, I would do the buffer ones first. I always do the harder problems first, so you can easily do the easy problems last. Calculate the pH of a solution that is boom, boom, boom. So they all have the same concentration at the same volume, which means very easy question. So HCl, is that going to react with my weak acid or the conjugate base? Conjugate base of NaF, I will get HF. An ice table is formed. I'll get one of this. I'll get 1.439. I'll get one of these guys. -1, -1, 0, because these cancel out. I'll get 0.439 plus 1 is 2. Do I still have a buffer left open? Do I still have a weak acid in its conjugate base? Which means I have to use Hasselbalch equation, which is pH is equal to pKa plus the log of A minus over HA. The negative log of 7.2 times 10 to the negative 4th plus the log of 0.439 divided by 2. Okay. Negative log of 7.2 times 10 to the negative 4th. That is going to be 3.14 plus the log of 0.439 divided by 2 is 0.22. The log of that number gives you an actual negative number. So negative 0.66. And you'll get C as an answer. Does that make sense? Okay. How do you do 32? Hey. What's in between 32 and 33? What's the difference? My hydrochloric acid gets way bigger, right? So I just undo a couple of things, right? Let's hypothetically just erase some of this because it's the exact same equation, right? So if I just erase all of this, put a 2 there, which one's bigger? Hydrochloric acid or base? So hydrochloric acid can be left over? So 2 minus 1.439 gives me 0.561. I don't care, I stop right at that process. That is my concentration of my strong acid now. And strong acids do what? So it's 100%, right? That is my concentration of my hydrogen ions. To find the pH, I do what? Negative log of 0.561. I don't care how much weak acid I make, I have strong acid. Much more important. Negative log of that number gives me a very, very small number, which should make sense, right? Because we were using HCl. That making some sense to you guys? So when the buffer breaks, it's pretty fun. It's pretty easy to understand what's going on. Cool. I know, isn't this great? So what is the value for KSP? KSP is equal to copper, fluoride, copper, not plus, we're multiplying them together. So it's going to be 4x cubed. I plug in that x value, and I'll get my KSP value. That's concentration. Yeah. Okay, what'd you guys get for 34? Because I got C. Huh? Okay, moving on. So 35 is very similar to the one we did with the MX thing, right? But in this time, I'm trying to figure out the number of concentrations of calcium. All right? Which basically means I'm trying to solve for concentration, which is basically the same thing as the X value. So if you do it mathematically wise, right? The one that's going to be the highest is going to be C. That's because it is 4x to the third is equal to 8 times 10 to the negative 6 power. If you solve for x, it's the biggest one. B and D are eliminated because they're exactly the same, KSP value-wise, and that they are not the same thing, so it doesn't make any sense, right? And that since this one is is the smallest one, it will give you the highest X value. Does that kind of make sense? Well, sorry, that's the biggest KSP. So the biggest KSP will give you the biggest X value. Sorry, my bad. I misspoke. I'm trying to get you guys out of here because I see you guys are losing the will to continue. I know. We're almost there. Of course. I love 13-hour work weeks, work days. Okay. I am sarcastic because I'm tired. Okay. I have an acidic equivalence point. So which one is stronger? The acid or the base for titration? The acid is stronger. So probably a strong acid with a weak base, correct? That makes sense? Because the acid is so okay. So I start all the way off here, right? So I have a strong acid. If I add a weak base, it's not going to do very much to it, correct? Because the acid is stronger than the base. It's going to take tons of the base and a long time before it goes off, right? So the equivalence point is going to, technically, let me draw it better. The equivalence point is still going to be below 7, right? Because it's going to take a ton of the base to neutralize the strong acid, right? Okay, that's why. So it has to be a strong acid with a weak base to get an acidic equivalence point. Okay, 37 is a bit weird to think about. Okay. If I add a if I add an acid, which is just a hydrogen to this guy, what acid forms? When H bonds to this guy, which out of the lead and fluorine, which one have you seen for an acid so far? You've seen HF, right? You've seen HF before. Is that a strong or weak? So if I add an acid to that guy, I get a weak acid, right? But I also get lead nitrate. This concept comes back from kind of Chem 113, but anything plus a nitrate becomes soluble. So the solubility is going to increase with that one. Yeah. So solubility is going to increase for the first one. Okay. So if I add hydrogen to this guy, what's the H going to attack? The PB or the BR? HBr. Strong acid. Does that want to exist? No. So that strong HBr is just going to form back into this thing, right? Did I do anything? The acid didn't do anything, right? It just made a bit of the same stuff. That's not going to change anything, right? So I want no change. The answer is E, because it's an increase, no change. So the reason why this one is a decrease in solubility, right, is because increase in pH. Am I adding hydrogen or hydroxide? Am I adding H or OH if I increase pH? I'm adding OH. If I add OH, does that make water? OH plus OH? Not really, right? It's going to decrease the solubility. However, if I take the exact same thing and add an H, the H plus the OH makes water, right? Which theoretically will increase solubility because it's making more water. That will increase. That's why that's like that. That kind of makes sense? If you have a basic solution and you add an acid to it, you increase the solubility because you're making water. If you have a base and you add a base, it doesn't really do anything. It's going to make it more basic, not make anything else. Okay. Sulfur is in the same column as oxygen. What's the oxidation number of oxygen? -2, right? So the formula looks like this. Which one of these guys looks like that guy when he's broken up? E is the correct answer because the 2 is attached to the silver, not the sulfur. Right? So B is wrong because that 2 should not be there. It should be on the silver, not the sulfur. Over 1 makes no sense. You're not dividing by that, right? No. So the answer is E. Okay. Almost done, guys. Home stretch. Woohoo. Okay, 39's a pain in my butt, and you'll see why. So, this is the KSP, right? I'm looking for grams. The X value for KSP is equal to moles per liter. So guess what I have to do? I have to first find X, divide by the volume, get moles, and then multiply by the molar mass. This is a very hard problem. I'm gonna do it out and draw it out. You guys in the classroom don't follow along because this is more for you guys to watch the video when you get here again. But KSP is going to equal MGF2 broken apart to MG 2F. That's going to equal to X concentration over 2X squared, which will lead to 4X to the third is equal to 6.4 times 10 to the negative 9th. Divide by 4. Take the square root of that. X is equal to, you're gonna miss the best ones though. Okay. So X is equal to, I believe, oh gosh, I can't remember how to do this. I can't remember the answer I got. All my work is all over the place. Oh no, okay. So that's, plug that in, divide by 4, take that guy to the 1/3 power. .0012 moles per volume. And then I'm going to take my 150 milliliters, change that to 0.15 liters. Multiply that by 0.15 liters. Cancel liters out. 0.0012 times 0.15. I get 1.8 times 10 to the negative 4th power moles. That times the molar mass, which is 62.39. Yeah, fun one, isn't it? So you finally get that many grams. That's how you do this one. I doubt this will be asked on your quiz. This one would take too long. This is a 3-step problem. It takes way too long to do this one. After the 1.8, I multiply it by the molar mass of magnesium fluoride. The temperature is going to tell us that the KSP is not changing. Okay. No. Yep. 62.39. Nope, you got to calculate it. You're given a periodic table in you guys' quiz, right? An exam. So theoretically, they don't have to give you molar mass. Okay. If you guys can muster up these last 4 problems, these are the most important problems of the entire unit. Because I can guarantee this will be your test is like. You'll see why. So first thing you should notice, 40, 41, 42, 43, and 44 all have the same answers. Right? So we're going to do things to this buffer solution, and it's going to change the pH. So first off, what is the pH of the buffer? Well, if you look at it, my weak acid and the conjugate base are the exact same volume concentration, right? So that's be 1/1 basically, right? So if I use the Hessel-Hasselbalch equation, plus log of 1, it's going to cancel that out. So I just take the negative Ka value and I'll get an answer. The Ka is 2.27 times 10 to the negative 11th. If you do that, you get the answer B. Now, you might think that B might not be used again. You are correct for this set of problems. However, it's a possibility that through some issues, I could get the same pH somehow, right? It is possible, very unlikely, but it is possible. So the rest of them, we can just ignore that part. We ignore B as an answer. Okay, for 41, what is the pH after adding an acid, right? So now, I'm gonna scroll all the way down because I need the room to do this. So now we're doing 41 down here. So we're doing 41 down here. So I have an HA. Oh, sorry, my bad. We're adding an acid, right? That's going to react with the conjugate base to make HA. Ice table. If you look at 41, is it the same concentration, the same volume as my conjugate base, conjugate acid? No, which means I have to make it to the similar unit, which is what? Moles. So, I'm just going to do the number. I'm not going to show you how to do it. You guys should know how to get the moles by itself. You're going to get 0.1 moles. You're going to get the exact same thing for all the rest of them, but it's 0.1. You change the 50 liters to 50 milliliters. 0.05 liters. 0.05 times 0.2 big M will give you 0.1 ml. That's what you'll get for the moles of those guys. With 41, guess what? The acid is also 0.1. So it all cancels out. Minus 0.1 minus 0.1 plus 0.1. Cancel out, 0, 0, 0.2 moles. However, can't have that, right? So I'm divided by the total volume. If you do the work, the total volume will be 2 liters. This will give you 1. Okay, I have HA left. I am given Ka in the formula above, right? So X is equal to the square root of the Ka, which was 2.27 times 10 to the negative 11th, I believe. Yep. Okay. I get an X value of 4.79 times 10 to the negative 6. Negative log of this number gives me 5.32 pH. That's how you do 41. Does that make sense? So 41 is that guy. Hey, what's about 42? I have double the amount of my strong acid. Do you guys see that? So I'm gonna have what left over then? I should have strong acid left over, right? And if you do the math, I can show you real quick. Boom, scroll down here. If, whoops. Okay. And then, Let's just select all of this. Hunky Mallory. Delete. All that. Hunky Mallory. Delete. All that. Delete. All that. Delete. All of that. Delete. Okay. Instead of getting 0.1, you'll get 0.2. So in 0.1, I'll get 0.1 of HCl left over. Strong acids do what? 100%, right? So that's my concentration of hydrogen now. So I'll just take the negative log of 0.1, which will give you 0.48. So 42 will give you 0.48. Do you see why I think this will pop up in the test? It's the exact same question, manipulated in different ways. This is what teachers love because they only have to write one question for one problem set for 4 different questions. I can guarantee questions like 40 to 44 will pop up on your quiz and exam.
Can't you assume that since you did the first correctly, you can just assume the next?
You can, but knowing Langley, he'll probably mess up somewhere. So it's good to show work anyway. But yes, you can assume. Okay. With 43, I'm now adding a base instead of an acid. And if you look at 41, 41 canceled out completely, right? With 40, so with this one right here, I'm gonna have leftover stuff, right? Which means I'm gonna have a buffer left over, right? Which means you're gonna use pH equals pKa plus the log of A minus over HA. pKa is 10.64 plus the log, if you do the math, is going to be 0.15 over 0.05. You take the log of this thing, you'll get 10.64 plus 0.48, which will give you what? 11.2. So lastly, you can justify that you'll get that left over. However, what's going to happen with this guy, with just like 41, right? They're going to cancel each other out completely. But instead of an acid left over, you're going to have to do Kb, right? Solve for the POH minus 14 to get the pH. Does that make sense? I'm going to draw it for the people on the Zoom, but that is the last question. What's the answer? Okay. Yeah. Yes. Just do 1.
You just assume it's the closest to 1/3.
Yeah. Negative log of 0.1. Oh, yeah. Yep. Yeah. Okay, I messed up. Sorry, I was trying to speed along. So you'll get 0.1 at moles, divide by 0.3 liters, you'll get 0.333 concentration, negative log of 333 will give you D.
Okay, thank you.
Yep, sorry about that. I was trying to speed along too quickly. Okay, I'm gonna draw 48 out for you guys in the YouTube videos and you guys on Zoom if you want to see it. If not, thank you for coming. But here's how 44 works out. NaOH plus HA will give you NaA. Ice table 0.1, 0.1, 0.1, minus 0.1, minus 0.1, cancel, 0, 0 plus 0.1, 0.2 moles divided by the total volume, which will give you 1 concentration. That's NaOH. So now we need to have, we have the base left over, which means we have to convert the Kw to Kb. So Kb is equal to Kw over Ka, which is equal to times 10 to the negative 14th divided by 2.27 times 10 to the negative 11th. 4.4 times 10 to the negative 4th. That is equal to x squared over HB. HB is 1, so just take the square root to solve for x. X is equal to 0.021. The negative log of 0.021 will give you a POH value of 1.68. pH is equal to that minus 14, and you'll get 12.32. Whoops, 12.32. That's how I get that answer. Okay. I'm going to stop recording before it gets way too long.